Hello, and thank you for viewing the Hunting with Security Analytics concept video. I'm Eric Heuser, and I work for RSA's customer-facing incident response team. In this video, we'll examine some of the concepts my team uses to find, among other things, C2 communications from malicious software. So when an analyst first uses security analytics, they're often overwhelmed by the amount of data they are presented with. This is common and happens to everyone when first opening the Investigate interface and encountering the wall of text. Navigating such a large and rich data set requires a bit of planning and additional data enrichment based on your organization's network layout. The first concept is directionality. So for this demo, I've created an additional meta key named SOC General. Now in this you'll see RFC 1918 source, dest, single-sided, zero payload, some other types of indicators. These are accomplished with application rules. So in here we can see this is a SOC General bucket, and we have RFC 1918 source and destination. Now in this demo data set, the internal IP address space is all RFC 1918 source and destined. There's no real IPs inside the organization. Your organization might use real IPs for tunnel interesting traffic ACLs, for land-to-land tunnels, possibly DMZs or other types of services. So if you have those in there, you might want to put them into a special bucket, and we'll see how we use them a little bit later. So the next concept is this zero payload and then single-sided TCP and single-sided UDP. It's worth calling these out because we're looking at interesting traffic. So along with directionality, we want to find traffic with payload and that has dual bidirectional streams. So this is because Trojan communications generally happen in the payload. So we want to kind of, if you're looking for a needle in a haystack, you want to remove as much hay as possible. So we have an application rule here for inbound and outbound traffic. So these will give us our directionality. And then our first carve concept is outbound traffic that is not single-sided and is not zero payload. We want something to look at. So in here we can see these are all applied to the data set and we can use them. So if we're going for inside to outside communications, which is the typical C2 communications, it's one click away. Now this is important to know that doing it this way at capture time is much more efficient than stringing all of these constituent parts together and making one large query. This speeds up query performance and allows you to select a single piece of meta for a very complex rule. Now if you were to try to run this type of query on the concentrator, it creates basically 3 queries and does bit masking because we store IPv4 as 4 bytes or 32 bits. So you would, every single query, it would have to do this sort of calculation across the indexes, which is pretty time consuming. But if you have it calculate at capture time, there's only one piece of meta and no calculations. It's a direct compare. So that's why it speeds things up a bit. So now that we have our inside to outside communications, we can start looking for things like HTTP beaconing, which is going to be covered in this. So there's a couple of different application rules that we've put together to detect HTTP beaconing, and it relies around how data can get up to a server, so through HTTP. Now you can't really put a whole lot of data in the header. You can do I'm online checks with a GET request, which has no body. So, but to actually substantially push any sort of data up there, you're going to have to use the post or the put method. And with HTTP 1.1 pipelining, we can get multiple methods in the same TCP session. Malware doesn't generally use multiple methods. They prefer a quick beacon in and then a new session. So, but when humans interact, like me interacting with this web application, there's a series of posts and gets based on what I'm doing, and it's over the same TCP session. So malware communications are typically thin. They're very short and small. They try to not generate a lot of bandwidth, and they're very simple. So we can go ahead and put and mark up the data set with service equals 80, action equals post, and action equals does not equal get. This will get us a post with no get. And we can do the same with get no post, and a post and a get. So we can see these pieces of meta here. Now we also call out the connect method, and that's sometimes used for tunneling. And if you have a post method, generally it has to come from somewhere. You can't just blindly post. So there's going to be a referrer. But malware sometimes doesn't have a referrer. And they can also be direct to IP. So we want to call those out specifically. And we have this down here, that TLD is com org or net or not com org or net. Now that's just, think of that as more like a tab, a bookmark. So you can divide up a data set when you get deeper into it. So let's go take a look. So we're going to just try, we have our first carve, and we're going to use HTTP post with no get. So that is our directionality and our little bit of behavior that we want to look for. So you can see from 17,000 sessions, we now have 652. So that's a significant data reduction. And we can go and look through either top-level domains. See, com, org, and net are the most common, and then there's other domains that are less common, top-level domains that are less common. So if we go ahead and just take a look, and anything that sticks out, as you start using security analytics more, you'll start getting a better idea of what common domains are, and if they're misspelled or similar to well-known domains like microsoftin.com or symantec1.com. Those kind of stick out. So right off the bat, we can see this ddos-ataky.com. This looks a little suspicious. So if we go and we look at the actual payload, we can see it's posting to a directory with this strange domain name, Opera 9.8, and just this little bit of data. So the server gives us a 200 OK, and then gives back something else. This looks suspicious, and this is very probably some sort of malicious software. It looks more like commodity malware, but we wouldn't know until we actually investigate the domain, say through virus totals, or look at the actual host itself and find the binary that's actually producing this traffic. And we can also see, based on a time, that it's periodic. So 1630.04, 1631.04, 32.04, 33.04, 34.04, 35.03, 36.03. Plus, it's speaking at every 1 minute intervals, plus or minus 1 second. So that's immediately suspicious. So if we look at some of these other domains, we can see architectural homes for sale, losangeles.com. Let's go take a look at these sessions. So in this, we can see it posting to viewtopic.php. There seems to be quite a few headers that you would expect, but the user agent is MSIE 6 on Windows XP. Now, I don't know of anybody who uses MSIE 6 anymore, so that's immediately suspicious. So it's posting 274 bytes, and this is non-ASCII data. So this is some sort of encoded or encrypted payload, and then it's getting a 404. So this certainly looks suspicious, and we should probably investigate this host. And again, we see about that's 9 seconds, 6 seconds, 8 seconds. But it looks to be posting roughly the same data, with just a little slight randomization, 5 or 6 seconds each. So this is malware as well. So these look similar. Architectural homes for sale Los Angeles, architectural homes for sale LA. I'm betting that this website was compromised at some point and uses command and control. So it's roughly the same data. So let's see, what else is in here that looks suspicious? So in this one, it's doing roughly the same thing. Posting binary data to this domain that is not familiar to me. Now this user agent is, again, Windows XP, MSIE 6, and SV1 is Security Center version 1. So this was released with the first service pack from Windows XP. So I believe that was 2004, and that it's 2016. And this PCAP was taken in 2014, so that means somebody's using a 10-year-old browser and operating system that have not been patched, and that's not that doesn't happen, especially in a corporate environment, unless it's a public Wi-Fi, and for some reason you're capturing that as well. So let's take a look at the periodicity. Again, it looks like about a minute, plus or minus, with this being the outlier. These two sessions here, and they're all roughly the same. So it looks like it is posting slightly different data each time. It changes in size. So this is certainly beaconing as well. So we can actually, instead of just looking at host names, we can come down here and application octet stream is for look at content types. The application octet stream is for binary data. There's text and HTML, text plain, application JSON. A lot of this stuff looks pretty normal, but application octet stream is generally used for encoded or encrypted data. So we can see these are all posts. Some of these paths look actually. So if we remember the first one we looked at, it was posting to a forum, and here it is. So it looks like these are all the same. And I'm willing to bet 11, 11, 11. These sessions all belong to this guy right here. So this is our German site, and then it immediately switches over to the architectural homes for sale. Then looks like this is still the architect. Oh, this is the shortened LA instead of Los Angeles. So it looks like this Trojan rotates through several different C2s, hoping to get some sort of response back. And it looks like it's beaconing every minute, plus or minus a few seconds. Another interesting aspect of Windows is the ephemeral or high port selection. So we can see these are sequential. Now, Windows hands out an ephemeral port in sequential order, for all connections. So if you see just beaconing like this to the same IP from the same source IP and an incrementing source port, that means the host is pretty quiet except for this connection. So you can see Windows is selecting the next connection up. So 11.15, 11.16, 11.17, 18, 19, 20, 21, 22. So this host is quiet, but that means there's no other activity. So a human isn't on there going and browsing around and doing their normal business. This is just another piece of software that's running, piece of malware that's running, that is constantly beaconing and trying to call back home. So another place we can go is there's destination ports. So sometimes if you're in an environment with a transparent proxy, a lot of malware, they know that you'll only forward, like, say, the common ports 80, 443, etc. Oh, that's IPv6 local, FE80. So I've seen Trojans where they were configured to connect out on port 81 because that was allowed out of the firewall, but not actually subject to the interception by their transparent proxies, basically sidestepping. It wasn't an intentionally made hole, but it was a hole nonetheless, and it is a tactic. So this is our German form Trojan again, but it's posting on 8080 as opposed to 80. So do I have a client? I do not. Another method, let's try this. TLD is ComOrgerNet and not ComOrgerNet. So let's go with not ComOrgerNet and see what else kind of pops out. This is our German form Trojan. I'm not sure what this is. Let's take a look at it. So again, we see our small short user agent posting to an unknown to me domain and with binary data. It doesn't look like it got a response back, but yet it still keeps posting. So this is certainly not human interaction with the internet, but some sort of Trojan. So if we take a look, 79, 78, 31, 33, 36. Doesn't look too periodic, but it still is all coming from the same host. So this would need to be taken a look at as well, because this certainly there's no response, so there's no actual HTTP daemon running on the other end. It's just not responding at all. It is pinning up the TCP connection because we have payload, but there doesn't seem to be any sort of real response back, which is also a little bit suspicious. So we can keep going down. I believe almost all of these are probably bad. And this looks to be a very similar Trojan, posting binary data that can't be read. Again, more of the same. Looks like it's another compromised form. So if we remove these, and we go back, another place I tend to look when I first get onto a data set is dynamic DNS. So this is used by quite a few attackers, nation state, crimeware, and everybody else, to quickly move and register domains so they can point to new IPs. TTL, the time to live for DNS lookups for dynamic DNS, generally are about 5 minutes, so they can give you the maximum amount of mobility. Now, we only have 3 sessions, so we can take a look at this. So this is going through this dynamic DNS. It's getting meeting index.html. It looks to be an older user agent. So there's looks to be encoded JavaScript and the script end tag. So this is pretty suspicious. All they're getting is a little bit of JavaScript when trying to go to index.html. Kind of makes you wonder. So the next session, that JavaScript activated the JVM, the Java Virtual Machine, as seen by this user agent. Now this is getting meeting applet.jar. So this user agent is getting a jar. So we can see jars are basically just zip archives of class files. So we can see the zip magic PK, and then we can see the actual classes in here. So the next session is a Java user agent again, this time getting meeting hi.exe. So, and this actually is poison ivy. So what we have for a Java exploit is getting this normal looking HTML page, heavily encoded JavaScript, and then seeing a jar come down by the Java user agent, and this is the exploit jar with the exploit class inside. It breaks out of the sandbox and is allowed to download an executable. And then if we pivot on this host, so if we pivot on this host, sorry for that, we can look at what else it did just after this. So we already have risk warning, poison ivy rat activity. So let's go ahead and find this. If we go and look at that, it's not going to render as text. It's a binary protocol. So you see we have the three-way handshake, SYN, ACK, SYN-ACK. And then this is what identifies poison ivy. It uses Camellia CBC to actually communicate, and when it authenticates with the client, it'll actually send a 256 byte key exchange and handshake, and that's where the password is encoded. So we can see the first request packet is 256 bytes, and the first response is 256 bytes. And then more random sized frames after the handshake is done. So this is a poison ivy exploitation, delivery, entrenchment, and C2 communications, all going over port 80 to this IP. So let's see, what else is in here? An encrypted RAR file, that's not as common as you would think. But it looks like so what this is it's a post to an ASPX. Now look at the destination. It is RFC 1918, and this is an external IP. So this is coming from outside the organization to inside the organization. And if we see what's in the actual post body, cookie equals, so this is the variable, response.write with these three characters here, which also shows up right here, and then eval and a base 64 encoded string. So this appears to be China Chopper, which is a web shell. It's a very, very small web shell that has it's a very small web shell, usually about 60 to 78 bytes, that that uses an anonymous code. So basically, you can send it a function, and it'll base64 decode it and the arguments and execute it on the system. So this looks like it was some sort of exfil attempt. So let's go back. And find this guy again. Find these IPs. So this looks like the output of a netstat command, and we can see it's in the inetpub www root. Looks like the attacker is running some net commands, some IP config commands, and some other domain commands. Now this base64 string right here is the actual function when decoded, and we can see here Z1 equals this bit in base64 and Z2 equals this bit in base64. So this is the function, and these are the arguments to the function that are being evaluated by the actual China Chopper web shell. And the actual utility that controls this puts in random X forwarded for headers to kind of throw people off the trail a little bit. So to look for this more efficiently, we can use the inbound traffic to actually find this type of traffic. And we can see that we have the Windows CLI admin commands, the RAR file encrypted, and that's pretty typical when you're dealing with a web shell. Now this web shell was over HTTP, which is clear text, and attackers are preferring SSL encrypted spots to put their web shells if available. Typical targets are Outlook Web Access and any other type of the service that you're running on the outside that's accessible. Outlook Web Access is preferred because it has to be a domain member and internet accessible. Now this means that it has direct access to your domain controllers typically. So an attacker placing a web shell in Outlook Web Access would have a clear path from the outside internet to the OS server to Active Directory because of how many ports and protocols Active Directory needs to communicate with in between these two machines. So that gives them another ingress way without using beaconing malware. So that's a quick overview of the hunting process that incident response uses to find some simple HTTP malware and simple HTTP web shells. I hope you all enjoyed it. Thank you. Have a good day.